Yes, I guess we can do that.
You're going to admit all?
Should we like wait for Professor Latifur Khan or?
That's fine. We
Yeah.
got 1 minute left. Yeah.
Yeah, I think we should.
Okay, so we have 1 more minute, right?
Yep.
Dr. Khan, is it okay if I admit all?
Yeah, please.
Okay.
Yeah.
All right, it is. I have already started recording.
Okay. Good morning. My name is Latifur Khan. I'll be your session chair. So we have 1 minute before we'll start the session. So in this session, we have around 5 or 6 papers. So the idea here is each paper will be presented first. Then if you have a question, please send me the question through the Slack. And then I will read those questions and speaker will try to answer those questions. So can you hear me? I hope you guys can hear me and see me, right?
Yes, I can hear you.
Okay, thank you. So in this session, the first paper will be efficient bidirectional order dependency discovery by Yifan Xing. He's a master's student at Fudan University in China. So his main research interest data profiling. So he's going to give a presentation. It will be a recorded presentation. Thank you. So please start the presentation.
Hello everyone, I am Yifeng Jing from Fudan University. It is my pleasure to introduce our work, Efficient Bidirectional Order Dependency Discovery. First, I will give you some examples to tell you what is order dependency. Here, there is a relation with 4 tuples and 4 attributes. When we sort these tuples by attribute A in ascending order, they are also sorted by attribute D in ascending order. So we can say A ascend orders D ascend. This is just an example of OD. The right arrow means ascending order, and the left arrow means descending order. As another example, tuples sorted by D in ascending order are also sorted by B, then break ties by C. We can say D ascend orders B ascend C ascend. This lexicographical order specification models order by clauses in SQL. Actually, OD is very useful in practice. An order by clause on an attribute without index can be converted to order by another attribute with index when they form an OD. Another usage of OD is to repair data. Unfortunately, order dependencies are commonly unknown in practice. It is impossible for domain experts to identify them in person. So we need an automatic algorithm to discover them. However, existing discovery techniques do not scale well or are not complete. So now we present a better OD discovery algorithm to resolve these problems. Now I will introduce some basic concepts related to order dependencies. The first concept is called minimality. The basic idea of minimality is that once we have found a valid OD, any OD that it logically implies is redundant. We don't want to discover any redundant dependency. For example, A descend orders B ascend D ascend implies A descend orders B ascend. So it is not minimal. And we also have the concept of minimal list. An attribute list is minimal if we cannot find any embedded OD in it. For example, A descend, C ascend, B ascend is not minimal if A descent orders B ascent is valid. As to minimal ODs, both sets must be minimal lists. Next concept is about violation types. Actually, there are two different types of violation when an OD is violated. I will still just give you some examples. Consider this relation and consider A ascent orders D ascent. T2 and T3 form a split violation because they are the same on A but different on D. T1 and T3 form a swap violation because T1 is smaller on A but bigger on D. Now, I will talk about how the search space of OD candidates are generated. This is called ExtendOD algorithm in the paper. Given an OD X orders Y and an attribute A overline, here overline means either ascent or descent. OD candidates are generated according to the validation of X orders Y. There are three cases. If validation result is valid, which means no violation, A is appended to the right, so we get X orders YA. If validation result is split, which means there is split violation but no swap violation, A is appended to left, so we get XA orders Y. If we can find any swap violation, no candidates will be generated. It can be proved that this strategy is efficient because it never generates duplicate ODs. To encode OD candidates generated by ExtendOD, represent an effective data structure, ODTree. An ODTree is implemented as a prefix tree based on ExtendOD. Compared to lattice used in functional dependency, tree is more familiar to us. We can design efficient algorithms based on trees. On this tree, each node represents an OD candidate. To construct this OD candidate, we need to follow the path from the root to this node. An attribute and the validation result of each node is recorded in the node to help us pass ODs and record the results. After encoding all OD candidates, next problem is how to check the states of OD candidate. So we introduce another data structure called sorted partition. A sorted partition, say tau x, is defined as a sorted list of equivalence classes based on tuple values on X. Tuples in the same equivalence class are equal on X. To save memory, sorted partitions only record tuple indexes. Expand and check are two operations on sorted partitions. Expand means to generate a new sorted partition on XY from two sorted partitions on X and Y. This is done by dividing equivalence classes in tau x into several smaller equivalence classes by their order on Y. Another operation, check, is to get the state of candidate X orders Y and get two violating tuples if it is violated. This is implemented by comparing maximum and minimum tuples in an equivalence class and between adjacent equivalence classes. As to check operation, it is very crucial that it just returns two tuples rather than all tuples involved in violation. Remember that every time I say violation tuples, that just means two tuples for each violated OD candidate. Now, I will present the framework of our solution called FindOD. The main idea of our solution is to decouple the number of attributes from the number of tuples. FindOD takes a relation R as input and discover a complete OD set, sigma of minimal and valid ODs of R. The first step of the solution is to sample. We get a very small subset R prime of R. Next, we use this small dataset, R prime, to conduct a full OD discovery and get sigma prime. This is an embedded OD discovery algorithm designed for small dataset. Then, we use R, the full dataset, to validate sigma prime and get violation tuples. Violation tuples will be added to R prime and begin another round of discovery. So step 2, 3, and 4 is an iteration. It terminates when we found no violation. Then we have sigma equals sigma prime. This iteration is bound to terminate because the size of R prime monotonically increases. Next, I will give you a brief introduction to sample, discover, and validate. That is our step 1, 2, and 3. Our sampling adopts a mixed strategy of random sampling and focused sampling. The first step is random sampling. We just randomly choose a small number of tuples from the full dataset, denoted as R1. In our implementation, the size of R1 is 1% of R. The second step is focused sampling. We use R1 to check all candidates in the form of A overline order sphere set, then collect violation tuples as R prime. This method is not expensive and it adapts to the data characteristics of R. Discover algorithm is designed to discover a complete OD set of subset R prime. Discover follows the breadth first search traversal of ODTree. In every iteration, we have to discover from scratch, since R prime has changed. For each node, we check minimality and branch non-minimal nodes. We check its states and then use ExtendOD to generate more nodes. Discover returns an ODTree that carries all necessary information for further iteration. And we use full dataset R to validate. We do not validate all valid nodes. We just want to check newly discovered ODs in this iteration. This time, we adopt a depth-first search strategy. The first step is to make a validation plan to make full use of intermediate result. Then, we still use sorted partitions to check. We check not only valid nodes, but also all nodes in the passes to them. We check all nodes in passes because when we find any mistake in the validation when we are checking a node that is the ancestor of one or more valid nodes, we can just delete all its descendants early. This algorithm returns the modified ODTree and the violation tuples for further iteration. Still remember that violation tuples means 2 tuples for each violation. This guarantees R prime keeps very small. There are more optimizations to our solution. First, we can reuse nodes whose state has been checked to avoid duplicate checking. Second, sometimes we don't have to wait discover to end, and we can start validate early in case its result is too far away from the truth. Third, we can build index for fast minimality checking. If you check minimality by brute force, that will finally be the bottleneck of the whole system. Finally, let's just have a look at the experiment evaluation. We compare our method named the final UOD with several existing order dependency discovery algorithms. We can see our algorithm achieves the best performance on most datasets. We can deal with all datasets within 2 minutes. We compare our method with order on both synthetic and real-life datasets to test scalability. We can see our method outperforms order by orders of magnitude on large datasets. Find UOD scales well on both the number of tuples and the number of attributes. As the number of attributes increases from 8 to 9, the time for order increases from 804 seconds to more than 5 hours, while the time for finding UOD only increases from 7 seconds to 9 seconds. This is all of my presentation. Thank you.
Thank you. Okay, and thank you. So let me check, is there any question? I did not see any question. So since there's no question in this at the Slack, so I want to ask you, you say something about the benefits of this work. What can you elaborate on that? So what is the motivation behind this work? So in your slide 2 or 3, you mentioned something, the benefit of your work. So if you can elaborate on that.
The motivation of the work,
Right, yeah,
is to discover order dependency in a quicker way.
Okay, quicker way, but okay, that's fine. Okay, so now thank you, the speaker, Zhang. So now we're moving towards the second paper, which will be, the title of the paper is Adaptive Network Alignment with Unsupervised and Multi-Order Convolutional Networks.
Hello, everyone.
Yeah, just give me 1 minute. So this paper is will be presented by Trong Nguyen. He's a PhD student at Griffith University in Australia.
Hi everyone, my name is Chung, and today I will like to present my paper, whose title is Adaptive Network Alignment with Unsupervised and Multi-Order Convolutional Networks. So my presentation will consist of 3 parts. The first part, I will introduce the network alignment problem and the motivation of our work and our contributions. In the second part, I will tell about our proposed method. First, I will give an overview of our method, and then I will describe in more details the two main components of our framework, which is multi-order embedding and alignment computation. In the third part, I will show the experimental results to show that our techniques outperforms other baselines in various scenarios, and then I will conclude my presentation. So first, what is the network alignment problem? So the network alignment problem technically is the problem of identifying the corresponding nodes across the different networks. So for example, you know that nowadays we have different types of social networks like Facebook, Twitter, and LinkedIn, and so on. And each social network will have its own function. So that's why people nowadays often have many accounts on different social networks. So it's a very interesting and challenging problem as well to identifying the accounts on different social networks that belongs to the same person. Besides social network analysis, network alignment also plays an important role in many applications domain like bioinformatics network or pattern recognition. So here's some challenges of network alignment community. So the first is the sparsity. So you know that nowadays the real world networks are very sparse. Like in social network, we know that Facebook have billions of users, but each users only have hundreds or thousands of friends. So you know that the network is very sparse, and which lead to the insufficient identity information. The second challenge is the heterogeneity. You know that like the network informations can come in different type, like the topology of network or the attribute of the nodes, like text or video and so on. The third challenge is the data availability. So you know that so in in network alignment or the ground truth data or the supervision data is often very costly to get and requires a lot of human effort. And the noise as well, which can lead to the accuracy degradation. And the last challenge is the scalability. So you know that the real-world networks is often very large, and it's why the time and the memory is limited. So, and for the existing works, so we can see that recently there are a lot of works that trying to solve the network alignment problem, and it can be classified into two main categories. The first category is matrix factorization-based method. So for this category of techniques, they aim to calculate the alignment result directly based on the matrix factorization formulation on the adjacency matrix. And you know that really the adjacency matrix is often very large, so that's why this type of techniques is often not scalable. The second category is the representation learning-based method. So first is they project the network nodes into a low-dimension vectorial embedding space, and then they use these embeddings to retrieve the element result. So this helps to overcome the scalability problem, but this type of techniques often susceptible to noise, fail to deal with heterogeneity, and require supervision data, which is costly. So in our work, we proposed a new representation-based alignment model, and in our model, we exploiting the multi-order nature of DCN to graphical convolution network to integrate the consistency constraint, as well as exploiting the heterogeneity of the networks, attribute and structural information. And we also used a jointly learning mechanism, which allows our framework to be an end-to-end and unsupervised model. And we also used the augmented learning process to make our models more robust to noise. And we conduct extensive experiments to show that our techniques can achieve a superior performance on real-world and synthetic networks, and also very robust to noises. So here's the overview of our techniques. You can see that there are two main components in our framework. The first component is multi-order embedding. The second component is alignment computation. So in the first component, you can see here, So we're starting from the source and the graph network, and source and the target networks. And we use the share weight model to embed the network nodes into embeddings. And we use multi-order embeddings in here. And then the embeddings are learned using the two losses, which is adaptivity loss and consistency loss, which I will explain later. And then using the embeddings, so we can first initialize the element matrix, and then refine using some criteria to make the alignment result better, and then we can get the final element matrix, which is the final result. The first is like before going into the details, so I will introduce about the graph convolutional network, and in our paper we also do some theoretical motivation. That's why graph convolutional network is ideal for network alignment problem. So the first is graph convolutional network is the work of Keith and colleague in 2016, and this paper received a lot of attention because of its breakthrough result. So it's technically a deep neuron model for graph embedding. So you can see that one graph convolutional network can have a lot of hidden layers, some hidden layers starting from the input networks, and have some hidden layers, and they use the message passing scheme on enable attributes. So you see that the next hidden layers is learned by the last hidden layer features, and with the neighbor set of these nodes. So using this message passing scheme, so they can integrate both the attribute information and topology information at the same time. And in our paper, we also give some mathematical proof to show that the GN embeddings can support commutation immunity, which means that even we like shuffle the graph and like commute the graph, but the embeddings is still the same. And it also helps to naturally support for the consistency constraint integration. So, but due to the time limit here, so I will not go into details into the theoretical motivation. And so the next is our multi-order embedding model. So we know that there is a trade-off between shallow and deep layers. So shallow layers bring more attribute information, and while the deep layers bring more structural information. And so that we, instead of using the only last layer, like normal traditional GCN, so we used own layers, the own hidden features, own layers at the embeddings for the node. So you see that in here, one node is associated with a set of embeddings, and we call that multi-order features. And we also changed the activation layer function from prelude to time to, because time is projective, and so that it mitigates the loss of information problem. And in here we use two different losses to learn about the embeddings. The first is called consistency loss. So it encourages the consistency constraint on the embeddings. So it technically is that the nodes that sharing the same information about attribute and structure, so it should have the same embeddings. And we also leverage the advantage of multi-order features. So it means that the nodes and the corresponding nodes should share the same embeddings at all layers. And we're also using the adaptivity loss here. So the idea is we use the perturbation-based network augmentation. The idea is we inject a small perturbation to the original network, to simulate the real-world noises, and we encourage the embedding to be stable to adapt to the simulate noises. So we can see the noise this function here encourage the stability of the embedding to the small noises. And the loss function is the combining of the two losses. And we also in alignment computation. So first we initialize the alignment result, which is the alignment matrix. So first we calculate the layer-wise alignment matrix, which captures the similarity between the embeddings of the source and the target nodes in each layer, and then we aggregate the final alignment matrix by the alignment matrix of all layers by the equation 7, and then we refine we base on the layer-wise alignment matrix and the aggregated alignment matrix. First, we detect the stable nodes and the unstable nodes. So the stable nodes are the nodes that having are close. So the having close similar embeddings of all across all layers, and otherwise this is unstable nodes. And we apply a noise-aware propagation, which amplify the stable nodes, the effect of stable nodes, and otherwise we when we calculate the embeddings, so we use this information to adjust the embedding. So the experiment is an experimental result. So we use several evaluation procedures like real-world performance, ablation study, effect of adversarial conditions, hyperparameters sensitivity, and qualitative analysis. And we use 6 state-of-the-art baselines with non-real-world data sets, and we run each scenario 20 times to avoid randomness. And you can see first for the real-world networks, so our techniques GLI can achieve superior like in terms of accuracy, which is very important for a network alignment model, while the time is acceptable comparing to other techniques. And we also like superior to the noises, like structural noises, attribute noises, and also another factor is the imbalance between the network size, we couldn't show here. And in the qualitative analysis, so you can see that, here's the embeddings of the nodes, which is nodes is in the moving networks. So we can see that with many order embeddings, with refinement having the best result, so because the embeddings are distinctive to each other. So in conclusion, so we proposed a new unsupervised network alignment, which used GCN-based multi-order embedding, and also a new noise adaptive mechanism with data augmentation, and we proposed a sophisticated alignment refinement, and we do expensive experiment to illustrate for our result of our model. Thank you for listening.
Yeah, thank you. Let me check whether I just checked 1 minute ago. There is no question at Slack, but let me check again. Since there is no question, I just request participants to send me some questions. For some strange reasons, participants are not sending any questions. There are 43 participants. So, okay, let me see. There is one chat. Okay, so I have a question for the speaker. So you utilize in your objective function, you utilize two types of noise adaptiveness and data augmentation. But when you report the results, did you consider each of their contributions separately? Can you hear me?
Yes, I can hear you. So yeah, I remember. So we were in the paper. So we already did that in the ablation test. So we test that we apply one version. We apply only one noise, one loss function, which is consistency loss, and another version. So we apply the both the losses. So yeah, so we did that in the ablation test in the experiment. So we can consider, we check that which loss contribute to the final result.
Okay, and at the beginning of your talk, you mentioned that graph can be heterogeneous. But when you did the experiments, you considered mostly homogeneous graph, or you consider heterogeneous graph? What I mean heterogeneous in this case, maybe the edge will be different type.
Yeah. So I mean that's the heterogeneity of information. So maybe the network nodes can have its own attribute, and and the structural information as well. So yes, for the heterogeneous graph, so there are two types. So it can encode the different type of nodes in the feature vector of the node, or otherwise, I think so. Yeah, so I mean the mostly the heterogeneous here is like the heterogeneous of information, like the heterogeneous graph. Yeah.
Okay, that's fine. Thank you. Actually, I changed the order by mistake. So now we are going to the original order. So the third paper in this session will be paper ID 96, Efficient and Diversity-Driven Ensemble. Yeah, go ahead. You want to say something? Okay, so in this session, we will have the our third paper will be paper ID 96, Efficient Diversity-Driven Ensemble for Deep Neural Networks. And it will be presented by Zhang, the student, and the speaker is a PhD student from Peking University in China. Thank you.
Everyone, I am Zhang Wentao, a PhD student from Peking University. Today, my presented topic is how to do efficient diversity-driven ensemble on deep neural networks. This is their content. First, let me see their background. Their ensemble of deep neural network is useful in improving their generalization accuracy in many practical applications. For example, by averaging the output of several-based models, their test accuracy can be significantly improved. But this also leads to high training budget because the training cost grows linearly with the number of the best models. And some models make this contribution due to their low diversity. As we know, the performance of ensemble learning can be affected by the following four main factors: the diversity, the number, the accuracy of base models, and the final combined strategy. So our motivation is how to get a fast ensemble framework which can get enough number of base models with high diversity and accuracy in a limited time. Next, I'll give a simple introduction to the related work, some diversity measurements, and the ensemble learning methods. For a classification problem, suppose the practical model output HEX is 1 if the sample X is labeled correctly, and -1 otherwise. Given an ensemble model H and the model weight of T, we get the ambiguity as the following equation. The key idea of this method is that the ambiguity term is related to the difference between the numbers of correct and incorrect votes. For a binary classification problem, we can simply calculate the proportion of samples with inconsistent prediction and then get the diversity of the given two best learners. By averaging the diversity of all pairs of classifiers, we can get the total diversity of the ensemble. However, all the above methods are too coarse-grained because they just use the predictor label, not the source-map output, to measure the diversity of ensemble system. More importantly, we cannot directly optimize the diversity during the training process with set of definition because we can't get useful gradient information. Now, let us turn to some ensemble methods. Compared with Adaboost, Adaboost.NC changed the weight update process by introducing the ambiguity term. For example, in the original Adaboost method, the correctly classified examples that the classifiers have the least disagreement on get the largest weight decrease, but in fact, they are supposed to be emphasized. So, Adaboost.NC consider this problem and use the ambiguity term to improve it. Snapshot Ensemble adopts a cosine analysis method to adjust the learning rate. In this way, it can escape and convert to different local minima. It saves the model parameters before resetting the learning rate, and treats each model replica as a base model. For example, as shown in Figure 2, it saves each base model every 50 epochs. For again neural networks, initializes each base model from a different random seed, and each base model is trained under the supervision of the earlier model. Let us analyze the limitations of the above ensemble methods. First, in Adaboost.NC, the definition of diversity is coarse-grained because it cannot make full use of the prediction. Besides, it gets low efficiency since it cannot use the prior knowledge. In Snapshot Ensemble, it gets low diversity, and the way to get diversity is not efficient and unstable. For Bohr-Again neural networks, it gets low diversity and accuracy. As shown in Figure 1, our method EDD can get the most balanced trade-off between diversity and accuracy. Now turns to our method EDD. A simple way to accelerate the training process is to use transfer learning, but to guarantee the diversity in ensemble, it is unsuitable to transfer all the pre-trained knowledge without selection. Fortunately, deep neural networks generally learn generic features in its lower layers and test specific features in its upper layers. Like Snapshot Ensemble, we accelerate the convergence of each base model by transferring the knowledge of the former pre-trained neural network. The main difference is that we just transfer the generic knowledge. So, the core problems we face is how to find that generic features, which is also equal to say how many layers of weight we should transfer from one pre-trained neural network to the other untrained one. To achieve this goal, we train a neural network HT-1 using the first N-1 folds and initialize the next network's HT according to the parameter beta. Then we train HT with the first N-2 folds. Finally, we predict HT's accuracy on the N-1 fold and the N folds. In the above case, the pre-trained network HT-1 has seen the N-1 folds while the next best model HT hasn't. Besides, the pre-trained network generally gets a higher accuracy on the N-1 folds than the N folds due to the overfitting. So we gradually reduce the parameter beta until the next best model HT performs similarly on these two datasets. In this way, we only need a few epochs to find how many parameters we need to transfer, which will not lead to large extra training costs. Now, let us see the diversity measure. For two networks, Hj and Hk, their diversity is denoted as the following equation. Note that Htxi and Hxi are both the source max output of sample xi, so their one known value both equal 1. For vector x, we have the following inequality. So the similarity of sample xi ranges in 0 to 1. Larger sim HT means model HT is more similar to model HK. At last, we define the diversity of the total ensemble networks by averaging the pairwise similarity of base models. To measure two ensemble models' diversity, we can save several base models with the same number of each group, and then calculate the DRV edge for each group respectively. Based on the diversity measure, we define a weighted diversity-driven loss function on sample X as following. It consists of two parts. The first part is the cross-entropy loss, which minimizes the training accuracy. The second part is to maximize the difference of the current model and the former ensemble model. For current model HT's output node C, we can get the gradient information by the following equation and then update the model parameters. This is our boosting-based training framework. We update the sample weights according to line 10. Larger SIMT xi means the current model HT has the same opinion with the former ensemble model HT-1 on sample xi. So we should increase WT xi more aggressively if it is misclassified. In line 12, we update the model weight by introducing the similarity term SIMT. Usually, the prediction of the ensemble model HT-1 is relatively more accurate, so HT's prediction becomes more important accordingly. To validate the effectiveness of our method EDDE, we conduct extensive experiments on the task of computer vision and natural language processing. The compared baselines are Borg neural networks, Adaboost.M1, Adaboost.NC, the Bagging, and the Snapshot Ensemble. Due to the time limitation, we will not introduce the concrete protocol and the training budget here. First is our effectiveness study, as shown in Tab 2. EDDE achieves the accuracy rate of 74.38% for outperforming the next best models, 72.17% under the same training cost. Table 3 shows EDDE only need half time to achieve the accuracy of 87.69% in IMDb dataset and 76.98% test accuracy in the MR dataset. As a result, EDDE is capable of getting a high ensemble accuracy with a limited training budget. Next is the end-to-end comparison. As shown in Figure 7, EDDE gets a higher test accuracy than other methods in all cases. More concretely, EDDE achieves an accuracy of 73.67% with only 130 epochs, while the next best model, Snapshot Ensemble, needs 400 epochs to achieve the accuracy of 72.98%. Which means EDDE is more than 3 times faster than the next best model. Besides, EDDE always gets higher ensemble accuracy than other methods using DenseNet 40. We can explain why EDDE works from the diversity perspective. As shown in Figure 8, the pairwise similarity of EDDE and Adaboost.NC is smaller than Snapshot Ensemble. Besides, from Table 4, we see Adaboost.NC can get the highest diversity, but it gets the lowest average accuracy. Snapshot Ensemble gets the highest average accuracy and the lowest diversity. So EDDE works well since it can get both high diversity and average accuracy. In order to show the influence of hyperparameters on EDDE, we vary its values and compare the ensemble accuracy. Note that the only parameter we should tune in EDDE is gamma, which controls the strength of the diversity-driven loss. As we can see in Table 5, EDDE with the setting gamma of 0.1 gets the highest accuracy of 74.38%. Even set gamma to 1, EDDE trained with 200 epochs still outperforms Snapshot Ensemble trained with 400 epochs. Therefore, EDDE is robust to hyperparameters. We add the ablation studies to show the effectiveness of our diversity-driven loss function and the knowledge transfer strategy. Table 6 shows that the ensemble accuracy may decrease if we use a normal loss function. Besides, we can get a higher average accuracy if we transfer all the pre-trained knowledge, but the diversity may decrease accordingly. On the contrary, if we remove the knowledge transfer part, we can get the highest diversity. For the Adaboost.NC with transfer learning, it can get higher average accuracy compared with the original method, but its ensemble accuracy is not as high as EDD due to its lower diversity and average accuracy. To sum up, EDD can get the most balanced trade-off between average accuracy and diversity, and it can get the highest ensemble accuracy. The last part is our conclusions. Firstly, we propose a knowledge transfer strategy which can accelerate the training process without reducing the diversity, and we also propose a method to efficiently select the generic knowledge which we should transfer. Secondly, we propose a novel diversity measure and use it to explicitly define a diversity-driven loss function. Besides, such a measure can numerically compare the diversity among its ensemble methods. Last, we propose a bootstrap-based framework to combine the knowledge transfer and the optimization process, and the static training pipeline can further improve the diversity. That's all. Thank you.
Yeah. Okay, thank you, the speaker. So do you have since for strange reason, I'm not receiving any question from Slack. So I would like to thank you, the speaker. Now we move towards the next speaker. So the next paper ID, paper ID will be 87 that will be presented here in this session. So let me tell you a little bit about more. So this will be presented by Wang. He is the presenter is a PhD candidate at Auburn University in the US, and the title of the presentation is A Natural Language Interface for Database, Achieving Transferability Using Adversarial Method for Question Understanding. So let's welcome the speaker.
Hi, thank you for joining me. My name is Wen Lu. Today, I want to talk about a natural language interface for database, achieving transfer learnability using adversarial method for question understanding. Recent advances in deep learning-based methods provide unprecedented ability to answer a natural language query against databases, but they still suffer from limited transfer learning ability. In this talk, I will discuss our work on advancing natural language interface using transfer learning and adversarial mechanism. Here is the outline of this talk. I will first introduce adversarial mechanisms since the transfer learning strategy is highly inspired by watermark adversarial attack. Then I will dive into the challenges, design, and experimental validation. First of all, I want to talk about why natural language interface to databases is an important research topic. As we know, we're living in a digital age, and data is accumulating on a daily basis. As a result, data analysts are often overwhelmed with more data they could possibly analyze manually. On the other hand, large-scale data has to be stored in databases, either relational or non-relational, and it requires certain knowledge to query a database. For example, relational database management system uses SQL, and the non-relational database MongoDB uses JavaScript. Consequently, there is an increasing demand for natural language interface so that users can query different data sets, different databases using just natural language. In this way, we are hoping we could contribute our efforts to bridge the gap between human and machine intelligence. In this talk, the objective of an NLII is to enable data analysts to probe the important trends in a data set. However, when it comes to natural language to databases, the entire system is often custom-made for a particular database. So how to overcome the complexity and the expressiveness of natural languages so that a single natural language interface can support a variety of databases is an unsolved problem. So in this talk, we will focus on transfer learning only, and we will not cover the topics like standard QA or speech recognition or dialogue systems. I want to first give a formal definition of the NLIDB task in this talk. An NLIDB should be able to understand the natural language question semantically, and they're able to translate the question to query language. And the resultant query language is executable with the correct information retrieved from the database. I want to first introduce the adversarial mechanism. Here we have two types of adversarial attacks. The first one is called backdoor attack. Supposing we have a well-trained deep model used for self-driving, if we feed a clean image to the model, such as a stop sign, it performs exactly as it's supposed to do, to say, hey, here's a stop sign, please make a stop. However, if we add a sticker somewhere carefully chosen ahead of time while training, you can make it anything you want. You can make it a yellow square, you can make a bomb, you can make a flower. Of course, such attack poses serious security issues for self-driving cars. However, such attack is very rare in practice, since you have to work for Tesla to add a backdoor while training. And the second one is more common in practice, which is an attack at test time. The images at the first row are clean images, and the second row are adversarial images. You can see some noise at the background. Such attack convinces the model that the background noise is very influential towards the prediction. Even though to human, the noise doesn't mean anything, but for deep models, it's a very strong signal for prediction. In summary, supposing we have a classifier F, the attacker can find a carefully chosen small perturbation, and after adding the perturbation, it will trick the model to make a false prediction with a very high confidence. There are several different adversarial algorithms. The heat map represents the background noise. All the adversarial attacks are trying to make perturbations towards the most influential directions. Inspired by such idea, we propose to use the adversarial mechanism to address the transfer learning challenge, and we will discuss the details later. I would like to describe the challenges we have for natural language interface to databases. I think most of the researchers would agree deep model does not support direct domain transfer. For example, if we have a well-trained model for sports domain, and we feed a question to the model, what's the height of LeBron James? The model is able to produce select height where player equals LeBron James, as it's supposed to. However, if we ask the model a new question, what's the population of New York City? The model is not able to answer this question since it has never seen the domain, the census domain before, and it doesn't know the meaning of population, and it doesn't know the meaning of New York City. Based on such observation, we propose a new strategy. That is to remove domain-specific knowledge to address the domain transfer challenge. Here is an empirical approach of removing such information. Supposing domain knowledge is known, we replace domain-specific data with predefined symbols. For example, in this question, we replace height with CO and LeBron James with V1. With such replacement, even the model is trained with sports domain, the input is not confined in such domain. With the same assumption that the model is well trained in the sports domain, given a new question, what's the population of New York City? After replacement, what the model receives is what's the CO of V1, and the model definitely has seen it before and is able to generate the correct SQL correctly. Based on the above observations, we believe the underlying logic or the latent semantic structure of the two queries are the same. What makes the questions look so different is merely the natural language idiosyncrasies for specific types of data. Motivated by the observations and the previous example, our goal, in summary, is to separate out data-specific components and focus on the latent semantic structure, so that domain-specific knowledge will not be a strong signal for prediction. And in our empirical design, what we did is to annotate the natural language question to reveal mentions of database columns and values so that different domains would share the same symbols and same SQLs. So here I will introduce the specific design of this paper. Like I mentioned earlier, we annotate the question to reveal mentions of database columns and values. Due to the powerful expressiveness of natural language, exact string match does not work here. For example, in this question, which movies were scheduled to release on January 4th? Movie and January 4th, 2019 can be easily tagged with string match. But we cannot rely on string match to match column release date with phrase to release on. Such matching requires contextual understanding. So we adopt a deep learning-based approach for our notation, which is contextual understanding. Here is an attentive bidirectional workflow. We have two inputs here. The first input is the question itself, and the second input is the potential mentioned column, release date. This is a binary classifier with output true or false. If the output is true, it means release date is mentioned in the question. The benefits of such model structure is that we were trying to understand the name entity release date while attending on the whole question. We call it contextual understanding since all the tokens are taken into consideration in a weighted manner. Supposing the model is well trained and it's able to recognize whether release date is mentioned in the question. However, the real problem is even I know the name entity release date is mentioned in the question. How do I know where it's mentioned? In other words, how do I know release date is actually mentioned by to release on in the question? The intuitive is that the phrase that mentions release date should be the most influential to the prediction. And the intuitive is made based on the following observations. For example, if we replace the question word which with what movies were scheduled to release on January 4th, the prediction will probably be the same. And supposing we replace movies with missions, which missions were scheduled to release on January 4th, the prediction will probably be the same. However, if we made a slight change on the phrase to release on, there will be a higher possibility that the prediction will be changed. I hope it sounds familiar because this intuitive is the same as the adversarial strategy where the adversarial direction is the most influential direction towards the prediction. Let's recap. Here we have 4 different adversarial mechanisms and take fast gradient value method, FGVM, as an example. It first finds the most influential direction using fast gradient method. Actually, fast gradient method is quite straightforward as well. It basically calculates the gradient of the loss, and it perturbs along the direction until an adversarial sample is generated. In this specific example, the prediction is changed from 8 to 4 However, we just want to find the most influential elements towards the prediction. Just like I mentioned earlier, I just want to find the most influential phrase in the question. So instead of doing actual adversarial attack, we borrow the idea of searching for the most influential direction. So we only use step 1 for searching to release on. And we define a function influential level to quantify how influential it is for each token. And we calculate the gradient of the loss inspired by the fast gradient method, and we calculate the L2 norm of each token. Here are real case examples from the real-world dataset VKSQL. As we can see here, the influential level of each token is able to pinpoint where the column name, like release date, is actually mentioned in the question. Here is our experimental validation. We compare our approach with several previous works, and our strategy achieves good performance by using a simple bidirectional attentive workflow. We also test our zero-shot transfer learning ability, which means the model was not trained for those domains where we test for direct transfer accuracy. And we observed that our model has robust performance with zero-shot transfer settings on different data sets. This concludes my talk. Thank you.
Thank you. Let me see, is there any question? No, there is no question, but let me ask you some question. So can you go back? You cannot show the result section, right? You briefly presented your result. So there, okay, so there is a mechanism called attention mechanism. So in your case, attention mechanism will not be useful at all because you try to identify the useful phrases, right? Or
yes, the attention mechanism is used in the bidirectional workflow.
Okay.
Yeah, so it's embedded in the figure of the model structure, but we have definitely used that.
Okay, and okay, and then what are the data set you use for the experiment?
For the training, we use VKSQL, and for transfer learning, we use overnet and the other data set called paraphrase.
Mm-hmm.
Yeah, we use 3 data sets in total.
Okay. Okay, and thank you. So now we are almost at the end of the session. This is the last paper. Paper ID is 824. Array-based. The title of that this presentation will be Array-based data management for genomics. And this paper will be presented by Ola Harova. The presenter is from Politico Milano University in Italy. So, and the presenter research interests cover distributed system, data management, and bioinformatics. Let's welcome the speaker.
Hi, my name is Ola Gorlova. Today I am going to talk about multidimensional data representation and its effect and optimizations on genomic applications. Genomic data management, from querying and analysis, is becoming the biggest and most important big data problem of the mankind. In the article called Big Data, Astronomical or Genomical, published in 2015, the authors highlighted that the genomic data will exceed the size of Twitter, YouTube, and astronomy data altogether by 2025. We are currently in 2020, and the increase in the data size expectations that have been set is so far true. At the same time, genomic sequencing started at a very expensive price, reaching $100 million, and now it dropped to less than $1,000. Some labs might even sequence your DNA for $200. How does a genomic data look like? So the DNA is just a sequence of letters which then processed to a region that has start and stop positions on the genome, chromosome identification, and the direction called strand. The data that we are using here is not the string information, but the interval information. This interval specifies where is this region in the DNA and what features does it hold. In 2015, GenoMetric query language was published. GMQL is a high-level query language for analysis of genomics data, concerned with multi-sample processing, annotation, and filtering of variants. It enables building new datasets from an existing using algebraic operations. It is implemented on top of a set of big data engines such as Spark, Flink, and SciDB. From top to bottom, GMQL has a layer of interfaces to other systems, a layer of abstraction of implementations using intermediate representation, and a layer of implementations. One of the implementations is done on Apache Spark using row-based data representation. In this work, we show the array-based implementation on top of Apache Spark. Let's talk about genomic operations that we will evaluate our model on. GMQL operations are extensions of classic relational algebra operations, plus domain-specific operations specifically responding to genomic management requirements. The domain-specific operations are most computationally intensive. Here is another example of how input data is represented in row-based format that was proposed in the article called Framework for Supporting Genomic Operations. This model is called Genomic Data Model, and it provides an abstraction for DNA regions. Regions of the model describe processed data, and it consists of multiple samples. They have a schema with 5 common attributes, and then the array of typed attributes. Here, the ID represents a patient sample. In our previous work, we proposed to adjust the genomic data model, the row-based one, to a new multidimensional array model, where regions of a dataset are stored into a single multidimensional array. Since genomic regions with the same coordinates can be replicated among the dataset, we reduce number of regions by having unique, non-replicated regions. This model has 3 dimensions. Dimension of samples, which is the patient sample. Dimension of region coordinates, which is only where the region is inside the DNA. And dimension of each feature represented by dataset schema. This model was proposed for a small set of operations under special conditions. In this work, we extended the model to the whole set of operations, eliminating the previous limitations and conditions. Now, let's talk about the implementation of the array data model. In the design of an internal data structure for arrays, we were inspired by Spark machine learning library. We proposed this implementation on Apache Spark, which later shows both performance and scalability of genomics operations. The core of the structure is the key value record in Scala, where the key is a quadruple of region coordinates. The value is further substructured as 2 paired arrays, where the former behaves as the map for accessing the later. As shown on the figure, each region key points to several entries of the replication vector. Their number corresponds to the intersample replication. In turn, the replication vector contains of pairs, sample ID and replication, where the later indicates the number of intrasample replications. Each entry of the replication vector points to an entry of the attribute vector. We divide operations into 2 sets, unary and binary. This presentation is just to give an intuition of the operations. More details can be found in the paper. Here we start with simple Unary operations: select, project, merge, and group. The input dataset is shown on the left side, and the result of each operation is shown after the corresponding arrow. This is how operations look like in the multidimensional domain. They are executed by first using the region key to perform data access, and then applying a function to its value, independently from the content of other regions, for producing the resulting region. In array model, the union operation is a merge of two arrays and a redimensioning. On the left side, we show an example of the operation. On the right side, we show the stages of the application for both row-based and array-based, where the operation 1 in the array-based is redimensioning, which is not needed in row-based. So this is a geometric join operation, which is join on intersection of regions. To speed up the operation, the implementation on the right side contains binning. Binning is a partitioning of the genome into segments of equal size, such that each bin is processed in parallel. We propose the array implementation of the join that performs binning on the array data type and performs redimensioning after the intersection. Our implementation for array shows higher performance than the row-based, especially when join is performed in a loop. Operation became more about redimensioning. We can see the map operation as an intersection left outer join. It also computes an aggregated value over cell values. Same as for join operation, it performs binning on the array data type and performs redimensioning after the intersection join. Geometric difference produces the result as what is in the left dataset and not in the right dataset based on the intersection. The last three operations have similar algorithms which allowed us to perform the same set of optimizations of those operations. They are computational intensive, and because of the array model, we have less number of keys to compare and intersect with, which leads to better performance. Cover operation is specific to genomic domain. It performs histogram of the region's intersections and then filter and merge the contiguous region based on given parameters. Let's start with the evaluation. We first compare the row-based and array-based implementations for each operation separately. For Unary operations, we generated a dataset contains of a total 23 million regions. For binary operations, we generated a left dataset that consists of 5 million regions. Then we used the dataset of Unary operations as right dataset.
Hello.
I think we lost the sound.
Yeah, we lost the sound, yes.
Yeah, I guess it's something wrong with the...
We got our benchmark queries from the below mentioned paper, as they are a set of simple and complex genomic specific queries. We have the best performance with the increase of the query's complexity. For example, the query CQ5 has a lot of binary operations that makes the computational complexity higher, and thus we gain the best performance with the array model over the row-based model. With the increase of data size, Unary operations scale linearly. Scalability for map and join is no longer linear, but this is to be expected due to the greater complexity of these operations with sizes. Here we show the performance of array-based and row-based solutions using datasets with approximately equal number of regions and size, but different replication factor. The array-based solution dominates over the row-based solution in group, map, join, and difference, and is dominated by the row-based solution in union. In the other operations, the array-based solution has better performance than the row-based solution with large values of the replication factor. The break-even replication factor is different for the various operations. It is smaller for select and project than for cover and merge. We next consider an AWS cluster of different size ranging from 2 to 16 nodes. The testing setup contained one driver node and 4 configurations of slave nodes, set at 2, 4, 8, and 16 nodes respectively. As you can see, the operation scales well with the increasing number of nodes in the cluster. So in this work, we show that by coupling the array data model with the Spark execution engine, we obtain a high-performance solution for supporting region-based operations for genomics. We covered the full spectrum of GMQL operations, and we designed an internal representation adapted to the needs of supporting region-based calculus within Spark RDDs. Performance analysis shows that our array-based solution is superior to a row-based solution in most operations and benchmark queries, especially with large replication factors.
Okay, thank you, the speaker. Let me see whether there is any question.
I have.
Yeah. Somebody wants to ask any question?
Okay. Yes.
Okay.
So.
Go ahead.
Also, you apply this array-based model to any real biological problem in genomics, and compared to other kind of models?
Yeah, we applied it for the set of benchmark queries. Those queries was set in some work, not by us, and they have the biological meaning, and we use them. And if you can go to the benchmark slide, you might see the comparison between those two models.
Okay. Thank you. And I have a question. So I saw at the end, when you presented the results, you show with the increasing replication factor, your algorithm performance, the array-based approach works very well. So what is replication factor here? Replication factor means like in Spark, they maintain multiple copies that you meant, or you meant something else here?
No, the replication factor in this case is the difference between the keys of two models. So if the row-based model have 1 million keys, then the array-based has 500,000 keys, then the replication factor is equal to 2. And so the greater the replication, the best performance.
Okay, and in Spark, people utilize caching to speed up. So did you use cache here? Cache means do you put the data in the main memory instead of the disk?
No, there was no caching the main memory.
So you rely on the disk? Or
excuse me, could you repeat?
No, my question is in Spark, you can do caching means you can put the data in the main memory instead of the disk. So that way you can speed up, or you can put the data on the disk like in the Hadoop people usually do. So
yeah, we don't use caching at all.
Oh, okay. Okay, that's fine. Thank you. Okay, and thank you very much to all of you in this session. So I think.
Excuse me, there is one more question in the public chat room.
Okay, let me see. Where is the question? I don't see it. Can you see the question? Can you read that question for us? I didn't see any.
Yeah, it's from Fortis. And the question is, how complex can the expressed queries be? We have seen examples of simple queries in the presentation.
Yeah, I think, is it for her or for, there is another speaker before her from Auburn. So she talks about NLP. I think that the question was asked to her, not to the last speaker. I have a feeling. Okay. But if the second last speaker is here online, she can respond to that question. This question is targeted to, I think, NLP to map into the NLP text to the SQL queries. So the example she showed is more simple queries. So if it is a complicated queries, how she will handle it? That's the question. So if the second last speaker from Auburn University, if she is here, could you please answer that question? If you are not here, that's fine. Oh, okay. I have a question for. Yeah, okay. I have a question for the last speaker. Since COVID-19, people are trying to do a lot of related to COVID-19. They're doing biosequence or gene expression analysis. So, are you planning to do something in that direction?
I'm sure we have people who are working more in the bioinformatics, like in the deep learning and machine learning stuff. But it needs to get the data first.
Oh, okay. Yeah, that way you can contribute for mankind. Anyway, yeah, thank you very much. So I will conclude the session at this point, and thank you for attending the session. So, and please attend the next session in a couple of minutes. Thank you. Bye now. Okay, bye guys.
Bye.